Section 8.1, Basics of Hypothesis Testing. A hypothesis in statistics is a claim or a statement about a property of a population. An hypothesis test, or test of significance, is a procedure for testing a claim about a property of a population. Here's an example. 1,009 consumers were asked if they are comfortable having drones deliver their purchases, and 54%, or 545 of them, responded no. Using P to denote the proportion of consumers not comfortable with drone deliveries, the majority claim is equivalent to the claim that the proportion is greater than half, or P greater than 0.5. The expression P greater than 0.5 is the symbolic form of the original claim. So we have this claim that the population proportion is such that it's greater than 0.5. Among 1,009 consumers, how many do we need to get a significantly high number who are not comfortable with drone delivery? A result of 506, or about 50.1%, is just barely higher than half. So we probably wouldn't conclude that that would be significantly high. A result of 106, or 99.7%, is clearly significantly high. But what about the result that we saw in this study of 545, or 54%? Is that significantly high? The method of hypothesis testing allows us to answer that key question. It's easy to obtain hypothesis testing results using technology. The accompanying screen shows results from StatCrunch, so we can use computers or calculators to do the computational heavy lifting. Using technology, which is what we're going to stress in this course. So here's some output from StatCrunch, and we'll learn about this further in sections 8.2 and 8.3. And here we see a test statistic listed there as a Z, and its value is 2.55 rounded, and the p-value in the last column is 0.005 rounded. What that tells us is something about the conclusion that we can make on the hypothesis test. I'm going to talk more about that in a minute, but focusing on how the test procedure works and learning the associated technology will then help us to better understand the results. Significance tests are also called hypothesis tests are also called tests of significance. In section 4.1, we use probabilities to determine when sample results were significantly low or high. This chapter will formalize those concepts. The null hypothesis, denoted as HO, is a statement about the value of the population parameter, such as a proportion, a mean, or a standard deviation, that's equal to some claimed value. The alternative is a statement that the population parameter has a value that differs somehow from the null. It could be less than, greater than, or not equal to. And here's a flow chart, and I'll let you look at that on your own, on how we're going to work on finding the results and setting up the hypothesis tests. So step number 1, you want to identify the claim to be tested and express it symbolically. In step 2, give the symbolic form that must be true when the original statement or original claim is false. Consider the 2 symbolic expressions obtained so far. The alternative is the one that doesn't contain equality. It's going to have either less than or greater than or not equal to. The null is always going to be a symbolic expression that the parameter equals some fixed value. So returning to the drone delivery, given the claim that the majority of customers are uncomfortable with drone delivery, we can apply steps 1, 2, and 3. Step 1 is identify the claim to be tested and express it symbolically, and we'd already done that. The majority is uncomfortable with drone delivery can be expressed symbolically as P greater than 0.5. Given the symbolic form that must be true when the original claim is false. So if this claim is false, then the opposite would be P less than or equal to 0.5. And then we want to identify the null, the alternative, and the null. So identify the alternative, and you're going to use a symbolic form here without the equal sign. And so that means we're going to use the P greater than 0.5 for the alternative, and the null is going to be P equal to 0.5. The significance level is the cutoff point for determining when the sample evidence constitutes significant evidence against the null. By nature, the significance level, which is called alpha, is the probability of mistakenly rejecting the null when it is true. Significance levels commonly used are 0.05, 0.01, 0.1. The most common is 0.05. Step 5 is what test statistic is relevant to the test and want to determine its sampling distribution. And in this course, we'll use the normal, we'll use the t distribution, and we'll also use a chi-square distribution. The claim that P is greater than 0.5 is a claim about the population proportion P, so we're going to use the normal distribution provided the requirements are satisfied. With n equal to 1009, P is equal to 0.5, Q is 0.5, and both NP and NQ are both greater than 5. Find the value of the test statistic and the p-value of the critical. The p-value of the critical value. We're going to focus on the p-value approach because we're using technology. The test statistic is a value used to make a decision about the null hypothesis. It's used by converting the sample statistic, such as p hat or x bar, to a score, like a z-score or a t-score. So basically, it's the number of standard deviations that your sample data are from the middle of the distribution. And if we go back to the drone delivery problem, and we do the calculations there, or we saw that in the StatCrunch output, the z-score, the test statistic for that particular problem, was 2.54, 2.55. So we're more than 2 standard deviations away from the middle of the distribution, which would be at 0.5 if the null were true. And the critical region is the area corresponding to all the values of the test statistic that would cause us to reject the null. And we can have 3 types of alternative hypotheses. Two-tailed, where we could reject either with a very large value of the test statistic or a very small value. Left tail, which is going to be the critical region or the rejection region, is going to be on the left side, so we're going to reject when our test statistic is quite small. And then right tail, the critical value of the rejection region is going to be in the extreme right tail, and we're going to reject the null when our test statistic is very large. And the p-value method is using a p-value. The p-value is the probability of getting a value of the test statistic that is at least extreme as the test statistic obtained from the sample data, assuming the null is true. So using the data from the drone example, the test statistic was z equal 2.55, and has a normal distribution probability of 0.005. So the right tail test with this test statistic has a p-value of 0.005. And so that tells us it's pretty unusual to get that particular result. Don't confuse a p-value with the parameter p or the test statistic p hat. P-value, and we're going to use a capital P to differentiate it here, is the probability of a test statistic at least as extreme as the one obtained given the null were true. Lowercase p is the population proportion, and p hat is the sample proportion. And the critical values actually designate where the critical region or rejection regions begin on the distribution. And again, we're going to focus more on the p-value approach, so I'm not going to stress the critical value option so much. So here's the decision criteria using the p-value method. If the p-value is less than alpha, reject the null. If the p is low, the null must go. If the p-value is greater than alpha, we fail to reject. And then restate the decision using simple and non-technical terms. So in our drone delivery example, there is sufficient evidence to support the claim that the majority of customers are not comfortable with drone deliveries. For wording that final conclusion, the next slide gives you some help with that. There's a condition on the left side and the conclusion that might be written on the right side, and I'll let you look over those on your own. Finally, do we accept or fail to reject? We should always say we fail to reject. We never say we accept the null. The term accept is misleading because it implies incorrectly that the null hypothesis has been proven, but we can never prove the null. Final conclusions can include as many as 3 negatives, and it's better to state it so that it's understandable. And you want to think about that when you're writing your conclusions. You can also use a confidence interval, and in fact, when you do a hypothesis test, it's helpful to do the confidence interval on the population parameter that you're working with to show how that decision of the hypothesis test is reflected in the confidence interval. In general, if you've rejected the null, the value hypothesized in the null will not appear in the confidence interval. If you fail to reject it, the value hypothesized in the null would be in the confidence interval. And finally, we can make mistakes when we do a hypothesis test. A type 1 error is the mistake of rejecting the null when it's actually true. And this is actually the alpha level or the significance level that we use on a test. The type 2 error is the mistake of failing to reject the null when in fact it's actually false. And we use the symbol beta to represent the probability of a type 2 error. And there's a little table that summarizes the type 1 and type 2 errors based on what the true state of the nature of the situation is and then what your decision is. So consider a claim where a medical procedure designed to increase the likelihood of a baby girl is effective, so the probability of a baby girl is greater than 0.5. Given the null and alternative, write statements describing a type 1 and a type 2 error. So here's what we were testing. So a type 1 means we're going to reject the null, and that's going to mean that we're going to lead us to say that in fact the medical procedure is effective when it really is not, that it's leading to an increase in girls when it really isn't. A type 2 is where we fail to reject the null when in fact it's false. And this would be where we conclude the medical procedure has no effect when it really is effective, increasing the likelihood of a girl. So let's try a couple examples. I'm going to give you a claim, and then I want you to write the null and alternative. So fewer than 95% of adults have a cell phone. In a Marist poll of 1,128 adults, 87% said they have a cell phone. So first we want to express the claim symbolically, and the claim is fewer than 95% of adults have a cell phone. So we write that symbolically as p less than 0.95. Step 2, give the symbolic form that must be true if the original claim was false. So if p less than 0.95 is false, then p greater than or equal to 0.95 must be true. And then finally, in the last part, we're going to write the hypotheses. And first you pick the alternative, which is the symbolic form without the equal sign. And that's going to be p less than 0.95. And then our null hypothesis is going to become the one with the equal sign. So p equal to 0.95, and our alternative is p less than 0.95. Identify the alternative hypothesis for each situation as two-tailed, right-tailed, or left-tailed. A national vital statistics report indicated that about 3% of all births produce twins. Is the rate of twin births the same among very young mothers? The key word here is the same, and that's going to be a two-tailed test, so our alternative would be written as not equal to. A magazine is considering the launch of an online edition. They plan to go ahead only if it's convinced that more than 25% of current readers would subscribe. So the claim there would be more than 25%, so that's right-tailed. A pharmaceutical company wonders if their new drug will have a lower side effect rate than the current 15% reported by the standard therapy. So the claim here is it less than 15%? Left-tailed. Decide if you would reject or fail to reject using alpha equal 0.05 and state a conclusion that addresses the original claim. The mean pulse rate in beats per minute of adult males is 72 beats per minute. The hypothesis results in a p-value of 0.0095. So since 0.0095 is less than the p-value of 0.05, we would reject. There is sufficient evidence to reject the claim that the mean pulse rate of adult males is 72 beats per minute. More than 58% of adults would like to erase all of their personal information online if they could. The hypothesis test results in a p-value of 0.3257. In this case, we fail to reject because the p-value is greater than 0.05. There's not sufficient evidence to support the claim that more than 58% of adults would erase all of their personal information online if they could. Identify the type 1 and type 2 error that results in the given corresponding to the given hypotheses. The proportion of people who require no vision correction is less than 0.25. The type 1 would mean we reject the null that the proportion of people who require no vision correction is 0.25, when in fact the proportion is actually 0.25. Type 2 would be to fail to reject the proportion of people who require no vision correction is 0.25, when in fact that proportion is actually less than 0.25.